Welcome to Schweitzer Drive, a podcast where we explore what goes on between the generation of electricity and the light switch. Join Dave Whitehead as he interviews the entrepreneurs, innovators, and experts who are inventing the future of electric power.
Welcome to Schweitzer Drive. I'm your host, Dave Whitehead. Today, we're diving into a new technology that turns aluminum into clean, dispatchable power. My guest today is Peter Godart, co-founder and CEO of Found Energy, a startup pioneering a new way to store and deliver energy using something we've had in our kitchens and airplanes for decades: aluminum. Imagine a fuel that's twice as energy dense as diesel, emits no carbon at the point of use, and can be shipped anywhere in the world using existing infrastructure. It sounds pretty cool. Before launching Found Energy, Peter worked as a research scientist at NASA Jet Propulsion Laboratory, where he contributed to missions like Mars Science Laboratory and Mars 2020 rover. He also led a team exploring aluminum-based fuels for potential applications in space probes. He holds a Bachelor of Science degrees in Mechanical and Electrical Engineering, a Master's of Science and PhD in Mechanical Engineering from the Massachusetts Institute of Technology. Hi, Peter, and welcome to our podcast. It's great to have you on.
Thanks so much for having me, Dave.
Okay, before we even get started in your cool technology, how did you get interested in engineering?
Oh, that's a great question. I mean, just since I was a little kid, I've always been taking things apart, putting them back together. Sometimes that thing would work after I put it back together. Sometimes it wouldn't. Learned a lot in the process. Then in high school, I started doing robotics. I'm from New Jersey, and we used to do this robotics competition that was sponsored by Panasonic, which was headquartered in New Jersey. And they would have these little competitions where you would have to solve these very complex challenges using items that you find around the house. So you would make wheels out of like wire spools, and they would give you a handful of Lego gears that you could use to make transmissions and all of that. But everything else, like popsicle sticks, had to be sourced from
So
the
this
house.
is a MacGyver thing then, huh?
Totally. Totally. And as you can tell, that's sort of been a theme throughout my career, is like, all right, let's see what we can make work with what we have in front of us.
Did you go to JPL after you got your bachelor's, and then did you go back to MIT for your PhD?
Yep, exactly. I worked there for 2 years and then got really excited about the technology I'd started working on there, which is a way of using aluminum as a fuel. And then wanted to pivot and do something a little bit more earth applicable, and saw going back to MIT and getting a PhD as a good transition period for that.
Well, that's good. Hey, let's actually get started talking about aluminum as a power source. How did you get interested in it, or what sparked the idea?
Yeah, so we were working on landers that may one day go to Europa, which is one of the moons of Jupiter. This is back when I was working at the NASA Jet Propulsion Lab, and we spent a lot of time discussing what would be the best power source. What's the best energy storage medium for these types of applications? And I remember just sitting there, we're discussing like, okay, well, do we think the next generation of lithium ion batteries are going to have 1,000 watt hours maybe per kilogram? And I'm just sitting there like, hey, you guys know that the aluminum that we're using to make these spacecraft actually is like 20 to 40 times more energy dense than any primary lithium ion battery. Why not use that aluminum as the energy carrier, especially when a lot of that aluminum you send into space is mostly there to survive the forces from launch and landing. Most of that's sitting around doing absolutely nothing once it lands. And so that was just that little spark of an idea that got me excited about harnessing the energy from aluminum metal. And it's just sort of snowballed from there.
So maybe we could spend a little bit of time talking about aluminum as an energy source. If you had asked me a few days ago, I would have never thought aluminum was a viable energy source whatsoever. So how does the process work?
Yeah, I mean, so aluminum, like any other material that could be considered a fuel, can be oxidized and basically can burn. And you can look at how much heat you get out of it per kilogram of mass that you burn. And for aluminum, it's about 8.6 megawatt hours per ton. It's a lot of energy. And where it really, really shines is actually in its volumetric energy. So if you look at a liter of aluminum, how much energy you get out, it's about 23 kilowatt hours. And that's 2x more than you would get from a liter of diesel. And so really the name of the game is burning the aluminum. So, how do you do that? Obviously, like your lived experience with aluminum is not that it's this dangerous, flammable material. I would challenge you right now to go grab a piece of aluminum, take a torch to it. Probably nothing will happen. Actually, I can guarantee you nothing will happen. And so the reason that nothing happens is that when it interacts with the oxygen, it forms a very stable oxide layer on the surface that does a really good job of protecting the underlying aluminum. So basically, it's like burning instantaneously on the outside, and then it just stops. And so at JPL, and then really during my PhD, I cracked the catalysis problem. I cracked the kinetics problem. So getting aluminum to react with not actually air, but actually water as an intermediate step, and basically circumvented this oxide layer issue by getting aluminum to essentially corrode or rust really rapidly in water. That actually generates hydrogen gas and a bunch of heat all at once. And then you can burn that hydrogen gas and steam that's coming off this reaction with air. And then you actually end up getting all of that energy out as superheated steam. So that was kind of the insight that enabled this process to work, is that, we can actually react it with water partially first and then with air. And so we discovered these catalysts that make aluminum break down in the presence of water and then proceed to react fully that way.
Found Energy describes the technology as rechargeable. Can you walk us through that?
Yeah. So, our process is basically undoing what we do to make aluminum metal. So aluminum is found in bauxite. It's actually one of the most abundant ores on Earth. Aluminum is actually the most abundant metal in the Earth's crust. We take that bauxite, we refine it into a material called aluminum hydroxide, and then that makes its way to aluminum metal via a massive injection of actually electrical energy. So we electrolyze that aluminum oxide, in that case, to aluminum metal. We're going the opposite way in our process. We're oxidizing the aluminum and extracting that energy. And our final product is aluminum hydroxide, which is exactly how you find it in bauxite. And so we can return that material back into essentially the smelting process to close that loop. But what's really interesting about our technology is that we are pretty agnostic to impurities. And so, you can think of what we're doing as aluminum smelting, but like the easiest possible version of that. You can invest electricity to make the aluminum metal. We do it in a process that's completely carbon free. And these processes exist. They're just not ready for mass adoption because, there are these issues around purity and scaling. And for us, it actually doesn't matter for us. So we are developing this concept of fuel grade aluminum, or like crude aluminum, that is actually cost effective, carbon neutral, and allows us to recharge that byproduct. So, in this closed loop process, we actually don't need to ever introduce new materials. We take a kilogram of aluminum hydroxide and we turn that into, about half a kilogram of aluminum metal. And then you react that with water, turns back into aluminum hydroxide, and you close the loop.
How, if you looked at the energy required to take the aluminum hydroxide and make it, I guess, pure aluminum, or as close as you can get before you turn it back into that hydroxide, what is all the energy you got to put in before you can get the energy you can get out? Is it like 2-to-1, 5-to-1, 1-to-1?
Yeah, even with the state of the art, kind of conventional aluminum smelting processes, you end up putting about 12 to 13 megawatt hours per ton. And then, like I said earlier, you get 8.6 megawatt hours per ton out. It's about a 70% efficient process, which is actually incredible for an electrofuel, an e-fuel. You're probably, some people might be thinking like, well, when I charge the battery of my phone or my laptop, it's maybe like 99% efficient. Like 70% doesn't sound very good. But actually, this just enables a completely different capability set than a battery. It's 40 times more energy dense than a battery. It's 1/1000th the capex. And so you can think of it truly as a fuel, which is more OPEX heavy and very low capex, versus a battery, which is very OPEX light, but extremely capital intensive to put together. And so, all of that for just 20% efficiency loss, is actually a really good deal. If you compare that to other electrofuels like, e-methanol, ammonia, any sort of synthetic hydrocarbon, it's actually, those are coming in the next best one at like 40% efficiency. And so aluminum smelting is actually quite good. And, it's sort of evolved this way just because it is so energy intensive to make. We've gotten really good at optimizing this process.
And now I'm just thinking about it. What about the safety aspects of aluminum and this process is versus a lithium-ion battery I'm carrying around on an airplane or something like that?
Exactly. The safety profile is obviously much, much better for aluminum metal. I always like to joke that you never heard of an aluminum spill or a billet spontaneously catching on fire. Now there are some cases of aluminum powders igniting and combusting. It's used as additives to paint to make it more reflective. And there have been some disasters there. But what we're talking about doing is big pieces of aluminum that absolutely have no safety concern whatsoever.
Where do you see the sweet spot for this kind of energy source? Would it be a good coupling with or replacement for a battery at like a data center that needs a handful of hours of ride through or something like that when they lose connectivity to the grid? Or where do you see the sweet spots, I guess?
Yeah, I mean, so I think our real sweet spot is just what I would call energy transmission. This is just a way to essentially leapfrog the grid, where you have some stranded renewable energy asset that's constantly pumping out green electrons. You recharge your aluminum hydroxide, you make aluminum metal, you ship that to some industrial energy consumer, be it heat, electricity, and then you send that back. So I think there is, a really good use case here for just continuous power delivery, and you don't have to worry about expanding the grid or overtaxing the grid, which these days can barely respond to the increased demand from these data centers that you're talking about.
Oh yeah.
But to your point, there's actually another really interesting use case, which is actually long duration storage. So not a couple hours, but think days to weeks to even seasons, because aluminum is much cheaper to make per unit energy than a battery, than like a conventional electrochemical battery. And the fact that it is, extremely energy dense and that it is completely stable. There's no self-discharge. You can leave it out in the rain. Nothing will happen. It's actually a great use case. It's just, you stockpile aluminum metal, you leave it there for months to years, and then you discharge it when you need it.
Would there be an application for electric vehicles?
So possibly on the charging end, our process requires a lot more balance of plant than, a conventional battery.
Yeah.
It probably honestly requires more balance of plant than even an internal combustion engine. We have pumps and solid transfer systems. And so for us, it really makes the most sense to go as big as possible.
Okay. So like maybe a ship or something like that.
Exactly. It's a dream of mine to run one of these massive container ships on aluminum fuel.
All right. So getting to that point, I guess you've mentioned that your system avoids the need for full electrification. And when we mean full electrification, what is that exactly?
So, there's always a debate around how do we decarbonize, right? Especially heavy industry is very difficult to decarbonize. And it's a very important sector to decarbonize because it's about 20% of global carbon emissions. Most of that is just going into heating water using hydrocarbons. And that is very difficult to electrify for a couple different reasons. One, it's difficult to get to very high temperatures with something like heat pumps, which are necessary because heat pumps, you get more units of heating out than you put in as electricity. Joule heating, you get 1 unit of heat for every 1 unit of electricity in. And so if you have cheap green electricity, fine. But, the grid is not overflowing, let's say, with abundant green electricity these days. And so, even if you could electrify the process itself, actually doing that transmission, that distribution is definitely not a solved problem. And so if you have alternative technologies that allow you to circumvent, leapfrog the grid altogether, that opens up a lot of flexibility. And so that's what I mean by you don't have to rely on electrification alone. we can just deliver clean heat behind the meter. Don't need to worry about expanding the grid in the short term.
So would that be where you see the market is behind the meter, or could you see utilities using this at scale?
I think, to start, we'll definitely be behind the meter. Think, consumer food and beverage brands, pharmaceutical brands, even some oil and gas companies that are, have massive operations, want to, if not decarbonize, at least make their processes more efficient. This gives them, again, that flexibility, that supply chain flexibility to deliver energy at a much cheaper cost and in a way that is much better for the planet. But, we definitely wouldn't stop there. Like these types of technologies only get more capital efficient as you scale. They follow these power laws where, your system will get 10 times bigger in terms of power output, but will only double in the cost. And that's definitely true for our approach as well. And so, honestly, like the thing that makes the most sense is to go utility scale and start talking about gigawatts. But we have a little bit of work to do before we can get to that.
Right, you got to have an ambition, right? You got to have a goal.
Totally.
Your roots trace back to space robotics. How did that shape the company's current mission and technology, or were they really just forks in the road?
Well, I learned everything I know about real engineering and project management and, setting lofty goals and executing on them from my time as a roboticist at the Jet Propulsion Lab. You're working on extremely tight deadlines when you have to launch something to Mars and your launch window is like 1 month every 2 years. And, if you scrub the mission, you wait 2 years, like the pressure's on. And, just had the great fortune to work with just some of the smartest people I ever met. That I learned way more in the couple of years I worked at JPL than really all of my years of schooling combined. So that definitely helped form who I am as a technical leader as well. But in terms of the technology roadmap itself, most of that was developed after my time there.
Here's an interesting one, and I have to deal with this quite a bit. What regulatory hurdles do you see with this kind of technology? That we get a lot of help from our government these days, sometimes more than probably we'd like.
Yes, I mean it's very interesting to design and build and scale a company around any sort of regulatory environment these days, just because it's changing so rapidly. And, we're seeing a situation where a few years ago we had all of these tax credits available for making green hydrogen, and, those are up in the air now. And so, we've really tried to build this company and develop these products and this technology in a way that doesn't rely on government subsidy. And so, we're trying to do this sort of on its own merit, without the need for any sort of like positive regulatory help. And then obviously like it's always a nightmare introducing a new technology to a very old and conservative market. And there you have to deal with like kind of the negative aspect of regulatory, and you have to abide by all these codes. And so actually it was a very important decision that I made as the CEO here, was to, after our seed round that we raised about 1.5 years ago, I brought in a beast of a VP of engineering who comes from oil and gas, like understands how to deploy new technologies in these environments. It's very conservative, but you kind of need that pressure. And so our VP of engineer, Angie, has been spearheading that. And that was a very smart move, because that's not something I would have been able to do on my own.
Oh, that's awesome. I bet she brings a wealth of knowledge to help you all out. If you had to, we talked a little about one of your goals. Wouldn't it be great to see one of these container ships running off of your technology? If you had to forecast out 10, 15, 20 years, what might some of those applications or technologies or use cases be?
Yeah, I mean, if you think about one of these, Panamax container ships, these are floating cities. They have 100+ megawatt power supplies, power plants on board already. And a lot of these ships you're seeing actually now sort of convert over to a more hybrid architecture, where it's still internal combustion based, motive power, but then that charges a battery and then use the battery to run an electric motor. And so you're seeing actually these much more flexible ship architectures. And you have a lot of space opening up for, to insert new technologies. And so there's actually a pretty clear path for us to start putting, an aluminum powered system on board. We make superheated steam. You can run a turbine and then you use that to charge the battery in sort of in the same way. So that's really exciting. What we're talking about, generally speaking, is actually using ships to transport aluminum around as a way of moving energy around. Why not just consume a very small amount of that aluminum on these journeys, and then you'll at least have solved the decarbonization for just that ship itself. It's still a pretty big problem. I think it's like between 3 and 8% of global carbon emissions, depending on who you ask. And so it's definitely worth pursuing. It's a $100 billion fuel market. Just for these container ships alone. So it's a very exciting application. Talk about conservative industries, though, like to get them to roll that out en masse, that's definitely going to be an uphill battle.
If I remember right, it's like, I think cruise ships, they carry like 3 or 4 different kinds of fuels depending on which ports they're pulling into or something like that. I wonder if this might be able to solve that problem as opposed to carrying all that different stuff around just so you can comply with some regulations.
Totally.
That's really interesting. Hey, since it is a thermal process, and we're talking about, steam turbines and stuff like that, how retrofittable would this technology be on, I guess I'd call it the front end of the plant as opposed to a coal pile or pick whatever else we're decommissioning these days?
Totally. This pairs very well with the coal piles, with like your just standard Rankine cycle coal fire power plants. We can basically replace the burner for those systems. There is, a lot of potential energy efficiency gains to be had, though, if you sort of design your own integrated like Brayton cycle, where you can essentially do this combustion inside a continuous turbine. And so this is something we're working on as well. It's not our beachhead market, so it's a little bit farther out. But yeah, the idea here is actually to be to be able to utilize as many of those old, soon to be stranded assets that you're talking about here. I think it's just fascinating in the U.S. that like a significant portion, I think definitely more than 50% of all rail lines are just to move coal around. All the rail lines that connect, that literally go across the country, form this amazing grid that we can hop on to just send aluminum. Aluminum, at the end of the day, actually has a very similar energy density profile to coal. Obviously, it's clean, so it's a no-brainer.
Hey, with these power plants, how dispatchable are they? Is it you build like a 300 megawatt plant, a gigawatt plant, and that's what you run it at? You don't go half power, you don't go more than that. It is turn it on, and that is the set point. So it provides like baseload, or is it really now you want to run 50 kilowatts? You run on a gigawatt. It'll just scale. You just put more aluminum in or whatever the process might be.
Yeah, I think, baseload is definitely easier to design around. And so that's obviously where we're starting. There's I would say there's no fundamental limitation to being able to ramp up and down. It's not going to be as dispatchable as an electrochemical battery, like nowhere close, just because, we want to keep the system hot. And there's some trade-offs, like you might have to resistively heat it while it's dormant, which it's depending on how long it's dormant, may or may not make sense. The technology, it's sort of like a gas burner in the same way. Like it's very easy to throttle it up and down, but it does need to idle.
Okay, all right, that sounds really cool. Any other thoughts about aluminum? Where you see this tech? Obviously, you're very excited about it.
Yes.
And you got some investors that are getting excited about it too.
Yeah, totally. Yeah, we've been able. So, this is a new technology. The average person on the street probably doesn't know that aluminum is energy dense, let alone can be used as a fuel. And a lot of the work we do these days is market education, which I know what I signed up for, and I'm happy to do it. And so, we've been fortunate enough to excite a great group of investors, and more importantly to me is actually inspire people to want to work at Found Energy, which is great. We have an incredible team, over 30 people, doing this hard work of scaling this new technology. So that I'm very proud of all of that. And the cool thing is like new applications just constantly come out of the woodwork. Like as we do this education, people are emailing us all the time, calling us saying like, hey, we have this idea here that you probably weren't even thinking of. And it ranges everything from like, weird esoteric aluminum waste management. There's a lot of aluminum that's very difficult to recycle. So like people are literally just sending us their trash constantly. And we're in the lab seeing if we can turn that into fuel, which is, very fun. Sometimes it's a little stinky. But there's actually been no aluminum we haven't been able to turn into fuel, which has been really interesting. And so, yeah, I mean, we're all ears. Like we understand what our go-to-market is pretty well. And, we're definitely as laser focused on that as we can be. But, I'm hoping that even folks listening to this will reach out to us and with some new ideas as well.
I hope they do too. We've always found customers will apply our products in ways we had never, ever thought of. Right. And so this collaboration between, technology you guys are creating and getting in the hands of some really forward-thinking, forward-leaning customers is always really exciting. That's what makes business so fun, right? Combining engineering and business it's just a great place to be.
Totally. And you find out at the end of the day, like, what problems are you truly solving? And that to me is kind of a fundamental difference even between academia and business is sort of, in academia and not to throw any shade on academics. I was one for most of my life. You can you have some more leeway to decide which problems you want to solve. And when you're in business world, then you have to succumb to the sort of the laws of supply and demand and capitalism. You find out like who cares about what you're doing very quickly.
I agree. But there's nothing more satisfying, I think, than coming up with some idea or some product or some solution, and somebody is actually willing to pay for it. Right? That is, that is so gratifying.
I love that too.
Peter, it's been great. This is really interesting technology. I'd love to catch up with you like in a year or so to see how things are going and how your product has come along. Excellent. Well, thank you very much for spending the afternoon with us.
Thank you, Dave. It was a pleasure.
Thank you for stopping by Schweitzer Drive. Join us again as we learn about, explore, and celebrate electric power. For more information about the show, please visit selinc.com/Schweitzer Drive.